let's start. Do you have any questions on what we did last week? I'm going a little bit slower than what I expected in the beginning, but I think we need to spend some time so that we understand what's going on in those models. So last time we talked about Clark and Scarf, and a number of references in your not required but recommended reading list has very nice approximations for the DP computation of Clark and Scarf. Now note that still the computational effort of Clark and Scarf is not that small, because basically what you need to do is you need to compute DP recursions, and it is not going to be very straightforward if you have nonlinear, still convex but nonlinear cost functions. Now, in that respect, a number of approaches have been created so that the functional equations, remember we had this G function that represented the cost of the lower echelon, lower installation. Just to approximate that function, certain approaches are given. One of them is by Song and Sheng, I think, if I'm not mistaken. And that's like a Nusswender bounds, which puts some bounds on the optimal solution so that you compute the optimal solution faster because you have some bounds, you don't compute certain states. So there are certain things that you can apply, but I think the idea is quite nice. We have we have n installation, and the way that we deal with that n installation is that we create an n-stage dynamic program, and we solve each stage in its own structure. Okay, so this is more or less the idea. Now, remember we said that Clark and Scarf is nice. It can be generalized. The only time that we cannot generalize it is the case where we have distribution systems. And when we have distribution systems, actually, it turns out that the allocation problem, the allocation of stock, in case of stock out, how are we going to let the second installation to satisfy the demand of the first installations? Now, this time we have a distribution system, is not very clear. So we are going to see certain things about distribution systems, which is related to this allocation problem. We're going to make some simple assumptions in the beginning, but then later on, we are not going to see any papers, but we will see that that problem can be resolved in a different way. Now, the Clark and Scarf paper actually is a periodic review paper, which means that we are considering items which are sold in large quantities. Now, when we are going to prefer periodic review in contrast to continuous review? Well, when our items are less valuable and we have large quantities of demand. In other words, instead of ordering each time that we have a customer asking for a Coca-Cola, we will never order a can of cola. Why? Because it's going to be too costly to do that. Now, what happens if you have items that are very valuable and the demand is not that high? In other words, we're talking about, specifically, we're talking about aircrafts and where the demand is for the items that require some maintenance. So thinking about the Turkish airline plane, okay? So what we are going to ask for is an altimeter. So the altimeters need to be replaced more frequently. Okay, the altimeter is the device that shows the height of the plane automatically. So we need to change those more frequently. But what do we mean by frequently? Well, frequently still means probably once in every 2 years. So even if you have 100 planes, the demand that you're talking about is probably 150 per year. So you have probably one demand per week. Let's say that it's quite expensive. And so what happens is that when we have a certain stock, every time that a demand happens, we are going to satisfy that demand. And moreover, we are going to replace that inventory. So these are the systems that now we are going to look at, like the maintenance for aircraft requires certain spare parts, but the spare parts are expensive, so we don't want to overstock those items. However, the existence of those stocks are very important because we're talking about something which is very serious. And in that respect, the policy that we use is going to be called S-1 S policy. What does this mean? This means that every time that we have a unit demanded, we are going to give an order for that unit. So this is the policy which is going to be applied. Remember in the paper by what was the first author? Turnquist was the second author, but I don't... No, not Append, the network one, the first paper that we have seen. Nordic and Turnquist paper. Remember they had an inventory policy that they applied. It was S-1 S-type policy. So when do you actually prefer S-1 S policy to, let's say, an RQ type policy? Well, you prefer S-1 S policy when the fixed ordering cost is relatively very low compared to the unit cost of the item. So we're talking about expensive items. So the paper that we are going to see by Sherbrooke, which I will try to summarize in 1 hour, is the so-called metric model. And the model actually deals with very expensive items. So S-1 S policy is a natural policy that you would apply for those items, which we usually call this type of a policy sometimes base stock policy. But base stock doesn't necessarily mean much because base stock means that every period you order up to the same level. But base stock here means that whenever you have a single unit demanded, you give an order. So it's a continuous review policy, and you continuously replenish your inventory when demand comes. Okay. Okay. Now, what does metric stand for? Metric stands for okay. Okay, metric stands for, oh my God, I started to forget things. Recoverable inventory control. My God. Oh my God, I don't believe it. Excuse me? Okay, let me see. In abstract, you said that there is... No. Metric actually is stands for the letters. Very simple. I'm sorry. It's a method for recoverable item control. Recoverable item inventory control. Okay. Now, it's not important, but this is basically the name. Now, it turns out that this is basically the start of a series of models which were applied in an Air Force kind of a environment in 1960s. And the main idea of these methods were that it took into account the fact that the items that we're talking about, the spare parts. So my altimeter example is not that good, but think about the following. We have this plane, an engine of the plane, there are, let's say, 2 engines of the plane, is an item that you want to keep in the stock. Why? because if there is something wrong with the engine, you are immediately going to replace the engine. The plane will continue on flying. So in that respect, having a spare engine is very critical. Now, what do you do with the engine? Well, if it was a Coca-Cola, we would simply throw the empty can. But you are not going to throw the engine because it's very expensive. So what do? You repair the engine. So the items that we are thinking of controlling are the items where repairing is the main possibility. So that's the reason why we have recoverable item. It means that whenever the item fails, it is going to create a demand for the new part. But in the meantime, what you are going to do with the failed item is that you are going to repair that item. So this is the main structure that is assumed. We have a depot, and then we have bases. So demand occurs in the bases, in a given base. Base is sort of a military term, but it can be like a retailer. It can be considered like a retailer. So a demand occurs here for the part. What happens is that there is a certain probability that that part would be repaired in the base. So we assume that Rij is the probability of repairing part I in base J. Now you can see that this part, each base might have different repairing capabilities. So it might be different, and of course there might be certain items that we won't be able to repair at the base. So if it is not repairable at the base, what we would do is we are going to send that item to the depot, and we know that at the depot it can be repaired. So the probability that it is going to ship to the depot will be 1 minus Rij, and with that probability it is going to be repaired at the depot. Now, question is, of course, even if we assume that these probabilities are known and everything is deterministic, you still have a long time, a probabilistic structure, which simply describes your resupply time. In other words, we do the following. We say that we are going to keep a certain level of this item at this base. Let's call that S sub j. In other words, we are going to keep a stack of S sub j units at any given time. This is going to be in terms of inventory position, of course. So what will happen? Whenever an arrival comes, it means that we require that engine, a working engine. If it is available in stock, we are going to supply it immediately. If it is not available, what will happen? If it's not available, we'll try to repair the item in the base. Okay? If it is repairable in the base, there is a certain repair time. If it is not repairable in the base, we're going to ship it to the depot. We're going to repair it at the depot. But of course, when we ship it to the depot might have a spare of that part, an inventory of that part. So what will happen? Immediately that part is going to be shipped back if it is available at the depot. However, if it is not available at the depot, what will happen? The depot will repair that item, and the first available one is going to be shipped here. So what we have is actually the time that it takes for the item which came as a defective item, and the time that it takes to repair it is not a deterministic value, but it's a random variable. It's a function of a number of things. So again, let me describe you the resupply process. Let's say that a demand occurs. Demand is going to be satisfied if there is stock at the base. Otherwise, what will happen? Otherwise, the demand is going to wait until the next item is available. Okay? Of course, there might be other demands waiting before. So in terms of first come, first serve, this item is going to go into a certain queue, and until its own turn comes back, it is going to wait. So if there is stuck at the base, it is going to be satisfied. Otherwise, it is going to wait for the first possible turn. Now, in that respect, when we look at this system, now I'm trying to draw an analogy between this and the lead time. Okay? What is the lead time to satisfy this demand if there is no stock available? The lead time might be the repair time here with this probability, or it is going to be, with the remaining probability, it would be the repair time and the resupply time from the depot. So what we are going to do now is we are going to analyze this system, try to write the objective function and so on, and see whether this system, how we can actually parameterize and then optimize this system. So this is more or less the structure that we have. Now, just to simplify the notation and everything, I'm going to assume a single item first. So Rj means that we have, this is the probability of satisfying the demand in base J. Excuse me, yeah. Probability that the repair can be done in base J. But you can see that we have this for multiple items. Now, the complicating factor is, of course, the following, which is not handled in this paper, but there are a sequence of papers by Sherbrooke. Well, later on, it turns out that Sherbrooke is sort of the main person, the key person in this research. He now has published a book in 1996, and he is the main consultant for the SAP for this type of optimization and for this type of systems. So he is sort of a very well-known guy. And this is one of his first work, actually related to inventory. There are some other work that he has done in probability structures. So given this, now let me specify the system in a more formal way. So we have, I will give some definition. So Rj is the probability that item can be repaired at the base. And then we have okay, and then we have Aj is the average repair time at the base. Oj is the shipping time from the base to the depot. Okay? So you can assume that this Oj considers a two-way track. So you have a certain resupply, you have a certain transportation time from the base to the depot. Now, of course, this is only going to be true, this is going to be the lead time if there is an item available at the depot. In other words, if there is an item available at the depot, what will happen? They are immediately going to ship that item. Okay, so this is going to be the time. However, if it's not available, then it is going to wait for the repair of the item at the depot. Okay, now let me talk about demand. Let's assume that lambda j is the demand rate. In the paper, they talk about the same model with a compounding distribution, which means that every time that a customer arrives, actually the quantity needed is not necessarily 1. Okay, there is a certain quantity which is defined as fj bar on the average which is needed. This is like the following. If you are going to replace one engine, what you usually do is you replace both engines at the same time, because there is always some kind of a balance in between them. So if you are going to replace, you replace both of them. So every time that there is an engine breakdown, it comes in doubles. Okay, so this is the logic. But let's forget about that. Let's assume that demand rate is given by lambda j, and it is a Poisson distributed. The number that fails has a Poisson distribution with this rate. Now note that, of course, when the demand rate is very low, Poisson is a good representation, which means that mostly it is going to come around the mean, but sometimes it has a very long tail, which means that it is going to take a very long time to fail. But it is usually going to be around its mean. That's the way to interpret the distribution. Okay. So what happens is that now if you look at each base, the demand rate in each base is going to be simply denoted by the arrivals. Now, how about the depot? When are we going to ask for the depot? Now, here in this type of a system, I am interested in the demand function at the depot. So the demand at the depot is going to be what? Let's say that we have j from 1 to n. Let's say that we have n bases. Now, with probability 1 minus rj, this is the probability that we won't be able to do the repair at the base. Then we are going to ask the base to supply us a part. So the actual demand of the base, of the depot, excuse me, is given by this term. So this is simply the depot demand. Now, if you assume that each of the base demands are independent, okay, then we are talking about the Poisson processes coming in, okay? So the total is also going to be a Poisson process. Okay, so this is more or less the one of the main things that is here. So here, actually, it turns out that if individuals are compound Poisson processes of a certain structure, then the sum is also going to be compound Poisson, but let's forget about that. Okay. Now, the interesting part is that if you didn't have S-1 policy, this wouldn't be true. How are we seeing everything from the depot? Okay, this is the way that we see in the depot. A demand comes in, okay, and using the decomposition principle of the Poisson processes, remember that? In other words, demand is coming in. So with some probability, it is going to be handled at the base. And with the remaining probability, it is going to be a demand for the depot. So what happens is that the stream also follows a Poisson process. Now, we are not accumulating the demand. In other words, we are not saying that, well, we have a batch size, and we have to wait until that batch size is filled so that we can give an order to the depot. No, our ordering policy is S-1S, which means that every time that a demand comes, we are immediately shipping it, if required, of course, to the above level, to the depot. So what happens is that this Poisson stream becomes a demand for the depot. When you have similar streams coming in from other bases, you add up those processes, that becomes a Poisson process as well. Now, if we didn't have S-1S policy, okay, this wouldn't be the case. In other words, here I wrote as depot demand, and this also follows a Poisson process. This statement wouldn't be correct if we didn't have S-1S policy. So this is rather simplification for general systems where we have batches. In other words, if I accumulate everything in batches here, then this wouldn't be true. Why? Because then it would be a different distribution. It will be some of, it will have some kind of an Erlang distribution actually. Okay? But in this case it is Poisson because basically you do everything in the same way. Now, the key issue here is, of course, then when I am going to keep stuck at the base level, or when I'm going to keep stuck at the depot level, the time that it takes to repair the item and place it back becomes the key lead time variable that we should be concerned. And that is called the resupply time. So what I'm going to do is, given that I have a demand, I have a certain time to satisfy that demand. In other words, I'm not going to order a new part from outside. I'm going to wait for that part to come back eventually. So the time that it takes to come back is the critical time that I have to consider when I'm keeping my safety. The worst case is the part comes here, you send it to the depot. Depot doesn't have any spare part to satisfy, any inventory to satisfy your demand. So what will happen? This is the longest possible time. And so, but there is a certain probability of that to happen. So you keep your inventory level using that resupply time, according to that resupply time. So this is what we're gonna do actually. Okay, now one result, remember we already mentioned about this result by Feeney and Sherbrooke. This is 1966. This result simply says that even if the resupply time has an arbitrary distribution, or can have an arbitrary distribution, only mean of that distribution and let's call this T is important when stockouts are computed. So remember, let's say that B of S is the expected number of back orders, and I'm sort of talking about either a base or the depot. That doesn't matter. This is very general. So this is, if you recall, the definition is if demand exceeds S, okay, then you are going to have a back order. And so this is X minus S, probability X given lambda tau, lambda T. So here the key is that if you have Poisson distribution or compound Poisson distribution for the probabilities, the parameter of the distribution, which is T, even if the resupply time or the repair time is stochastic, you are only concerned with its expected value. Remember, this is the solution, this is the result that they used in the first paper as well, when they were computing the S values, the safety stock values for the Nozick and Turnquist paper. Okay, this is the result that they utilize actually. But remember, I told you that like their result is reasonable if S minus 1S is a reasonable policy. In their structure, actually, they were talking about an arbitrary system. S minus 1S is not that meaningful because the items are not that much expensive, even if we're talking about automobiles. Okay? In other words, every time that a customer comes, the whole system moves is not very reasonable in general. But here in this case, of course, with respect to the items that we keep in stock, this becomes crucial. So note that here this t is just the expected value, and this is sufficient to represent if this distribution is Poisson or compound Poisson. Okay? So if this is Poisson or compound Poisson, this result is true. So this is going to make our life simple, because this means that we are not necessarily going to compute the distribution of the resupply time, but just to compute the expected value is going to be sufficient. Okay? So this is actually a very important result. Okay, so let us see what will happen. Well, we have some other properties of this function as well, but let me first elaborate on certain terms of the model. Okay, now let's say that, okay, depot has infinite stock. Okay, remember the structure, and let's say that depot has infinite stock. What does this mean? This means that whenever a base sends an item for repair, okay, there will be no delay. They will immediately ship it. There will be no delay with respect to repairing an item, finding another item, so on and so forth. So in that case, so the resupply time will be OJ. Remember, we are only going to pay the transportation time. Now, what happens if depot has zero stock? Now, this means that the depot is going to repair the item. So there will be shipment, of course. Again, you have to ship the item. But then there will be a certain repair process, and then the item will be resupplied. So what does this mean? If it has zero stock, it means that we have to wait for the repair process to complete its cycle, and so that we can have our part back. So we are going to have this D, and this D is defined as the average depot repair time. Now, I am going to talk about this in a while, but this D is assumed to be the average time. So whatever you have in the depot, you have some kind of an average time that you expect the repair process to take. Note that it might have a distribution, of course, but we are only interested in the averages because of the result that we have here. Okay, so it means that if we send an item to the depot is going to satisfy it in a time which is going to be in between these two times. The worst case is we are going to wait for the delay. The delay might be very long, of course. We don't know that. Or if depot has infinite stock, it's not going to have any delay. So this D stands for actually a delay, but it has a certain distribution. Any questions on this? This is sort of the range. So if we keep S0 inventory levels or inventory position at the depot, then the time is going to be an element of OJ plus D. So we know that the resupply time is going to be sometime in between. So using this fact, what we are interested in is as follows. Now, first of all, let's compute the expected number backordered. This backordered actually is not necessarily a good word when we're talking about the depot, but expected number of, or let's say expected number of, let me use the jargon, expected number of units in resupply when there is a delay will be what? So I'm interested in this B function that I have here. And so what I have is I'm going to have S0. Lambda is the demand rate. D is the resupply time, the repair time. Now note that if I'm shipping, this is just a constant time that I have. It doesn't affect the operations at the depot. Because if you have one, you will simply give one. The important part is what is the total demand that can come during my repair process? Because I will be interested in that so that I'm going to decide on S0 accordingly. So this is actually what I will be interested. This term is simply summation S0 x from S0 plus 1 to infinity x minus S0 P of x lambda t, where lambda is actually the lambda that I have written here. So let me specify this lambda. Lambda is going to be I from 1 to n, 1 minus Ri lambda I. So this is the rate that demand comes to the depot, and T is actually, in this case, T is going to be replaced by D. Okay? So during the repair process, this is the number that I expect not to satisfy at the depot level. Oops. Now, this is the probability that I need to compute, and so what this means is basically the following. And so if I want to compute the average delay per demand, then I'm going to approximate that average delay per demand by this function. So I'm going to have Bs0 lambda d divided by B of 0 lambda d. What is this? This is the backorder that I'm going to have, the number in backorder, when I don't keep any stock. This is going to be the expected number of backorders that I'm going to have at the depot level when I keep stock of S0. Okay? So this ratio is always less than 1. And times D is going to be what I'm going to write as the average delay. Now, and this is actually, I'm going to define as delta S0. So this is the approximation that it does. Now note that this term that you see here is going to be the expected number of backorders that you are going to have during this D period. Now, on the other hand, what I need is, whenever there is a demand, I need the time that I'm going to wait. Okay? For me, the time that I'm going to wait from the base is going to be important. So how am I going to convert this? Basically, this is the approximation which is used to do that. Note that if you don't keep any stock, this expected number of backorders will be at its maximum level. As you are keeping a stock, okay, this is going to be the expected number of backorders that you incur. The ratio which will be always less than 1, okay, and it might be equal to 0 as well, of course, then you're going to have a delay. Now, when is it going to be equal to 0? When is this delta is going to be equal to 0? When infinite stock. When we have infinite stock at the depot, okay, we are not going to have any delay. If we have 0 stock, this is going to be 1. So what we do is we assume that this is the function that represents the expected time, expected delay that will incur per demand. So this is actually the main approximation that they do. They simply say that this ratio is a good representative. But we don't know whether it really is the exact term or not. But how are we going to use this? Well, the way that we are going to use this will be as follows. Let Tj be the resupply time for depot for base J. Now, in this case, what will happen? In this case, I'm going to be able to write T in the following way. Now, with probability Rj, or Tj, this is Tj, with probability Rj, I'm going to have the resupply time as Aj. What was Aj? The repair time at the base, plus, with 1 minus Rj probability, I will ask the item from the depot. Now, I know that the resupply time will be at least Oj, because there should be a physical shipment time, plus, depending on the stock availability above, so let's write delta S0, I'm going to have an additional delay. Yes? Okay. Now, usually, you see, the critical issue is that if you have a part, it is going to go one way. In other words, if the depot has this part, it's only going to ship from the depot to the base. Now, on the other hand, if you do not have that part, okay, it should be a, well, two-way kind of a description. So let us assume that this D is selected so that it is going to take that transportation time into account. Okay? Because you see here, the critical issue is that if the depot has, you are going to give them a phone call, so they are going to ship you before they actually receive your damaged part. Okay? So we are assuming that this D is going to take into account the time that it takes to receive the item, the defective item at the depot level, and so on. Okay? But you're right, actually. Actually, Sherbrooke talks about those type of details. If you look at the paper, the first 10 pages is actually how are we going to apply these numbers, how are we going to estimate all these figures, so on and so forth. So it is a very instructive paper in the sense that it describes everything in a lot of detail. Okay. But this is sort of the key. So what this means is that now, as I'm going to be interested in my back orders, so the back orders at the base level, now I can write B sub j, S sub j. Let's say that this is the back orders at the base level. Then this is going to be simply, I will have lambda j, which is the demand rate, and then I will have the TJs coming into picture. So my resupply time that I will be interested will be computed over this TJ. So this is more or less actually the key issue in the paper. Now, what am I going to do with this? Sherbrooke talks about a number of different types of objectives, but the objective that we are going to have in this paper, I think is, well, he talks about several different issues. It's a little bit complicated and at that aspect if you read the paper. He talks about the way that they implemented the project versus the capabilities of the model. So the way that they implemented was very simple. Because they had a certain total stock, they tried to minimize the back orders given that total stock, which means that if you have a total of, let's say, 100 stock, how many units are you going to keep at the base level? How many units are you going to keep at the depot level? They minimized, actually, they took as given and minimized the back orders. Okay, so you can see that this is more or less what they have done. So the objective is rather different, but the typical problem that is solved in this case would be the following. You minimize over Sj's in general and S sub 0 the, let's say, the j from 1 to n of Sj, you minimize the total stock that you are going to keep, plus S0. So this is actually what you minimize. You minimize the total stock. If it is single item, actually. If it is multiple items, then you are going to have the unit costs added. So this is the total system stock. This is the amount that you keep at the basis. This is the amount that you keep at the depot level. Subject to, you want a certain service level. This is actually what you would do. The service level is, of course, let's call the service level as B sub j. It is going to be a function of S0 and Sj's, and you want this service level to be, I don't know why, less than Bj for all j. In other words, you have constraints on each base. Actually, this is service level constraint on each base. You want that service level constraint to be satisfied given the allocation of S0 and Sj. So you can see that Sj is, they are interrelated to each other. It's not that simple. How are we going to come up with this beta j? Well, this Bj gives me the expected number of orders, which is a function of Sj and S sub 0, which comes from Tj. Remember? Okay? So it is rather complicated, and the computation of this model can be done by the so-called Lagrangian technique. I'm not going to talk about that, but there are very efficient ways of computing. Now, two things that I'm going to say. Number one, of course, this is sort of the first round model, and there are many models which follow this one. And this issue can be resolved if the distribution of demand is Poisson rather than compound Poisson. You can exactly actually compute the average delay per demand. It is done by Graves in 1985. So after maybe like 17, 18 years. And then the key issue here is this assumption here. Now, what kind of a maintenance system, repair system should we have so that we can write this as D bar? In other words, what is a typical maintenance system? Let's say that you have parts coming in. You have a certain repair shop, and how do you treat the items? Let's say that you treat the items on the first come, first served basis. So eventually what you have is you have a capacitated repair system. And unfortunately, when the system is out of stock, in other words, when the depot is out of stock, what will happen? All the demands that will come is going to start waiting. In other words, it is not independent. In other words, in cases where you will have a lot of repair requests are the times where you don't have any stock left. Okay, so they will be at some specific periods only. So writing this as D bar, as D, which assumes that you have a delay, an arbitrary, an average delay, is not true because that delay is not independent of each other. So there is actually a queuing system in reality which operates that. So this delay is probably much larger in those instances. Okay? So to compute those, you need to solve this problem, whereas in Sherbrooke, it is assumed that this delay is actually known and is a constant. So he implicitly assumes that there are infinite repair people, and the repair can be done in parallel. So this becomes the assumption. Whereas from queuing theory, we know that the delay is going to accumulate. If you have a lot of people coming in at the same time, the delay of the first one is going to be dependent on the delay of, well, the delay of the second guy is going to depend on the delay of the first one, so on and so forth. The delay is actually a correlated process. So this is another assumption, which is not correct, actually. And this can be done in an exact term. However, this whole idea of writing everything in expected terms is very nice and simple. And metric is actually, in that sense, one of the first real multi-echelon systems. And of course, the knowledge now is a little bit more than what I have written here. Okay, any questions on this? And this is the extent that I want to talk about the metric model. After the break, I'm going to start to the so-called the allocation problem. Okay, any questions again? Okay. I'll see you in 10 minutes.